Hello, my name is Jansen and I want to give you a brief tour about pyiron. Pyiron is an integrated development environment for computational material science. We start here on our website, so pyiron.org. You can browse our code on GitHub, you can install it directly from Conda, and if you scroll down, you can try it directly on my binder, and that's what I'm going to do for this demonstration. So I click on this try pyiron on my binder link, and this takes me to my binder. My binder is a public service where they basically build Docker repositories or Docker containers based on Git repositories, and we're going to use this service now for the pyiron demonstration. As it's a public service, it sometimes takes a while to load. To see the progress of your Docker container, you can basically click the show button here, and we see it already found in precompiled image, and it's now launching the server. So we should soon get our running instance, and then we can start to jump right in. While this is loading, maybe some brief words about pyiron. So the goal with pyiron was really to develop a tool to develop complex simulation protocols. So whenever you try to run bigger calculations, and in our case a lot of ab initio thermodynamics, we really struggled to build up this kind of complexity based on shell scripts, and then we identified the Jupyter environment as a perfect place. So when you start my binder link, you're greeted with quite a series of different examples. You can go through each of one, maybe starting with the first steps and then look at the other ones depending on what your interest. But for this demonstration here, I would like to start with a blank, very clear new Jupyter Notebook. So we just open a new one running Python 3. So it's loading again. Yes, now it started. So let's call this demo for a demonstration. Right, so to start pyiron, we can begin by just from pyiron, we import project object, and then we create a project object instance, just giving it the name. So here I name it demo as well. Executing the second line already creates a folder. So that's what we see here. And we have this demo folder. Jumping back into the notebook. The goal was really to do as much as possible from the notebook. So we can now also see the path here, but that's commonly not needed for the user. So having now a project object, we can create other objects from this project, and with this we directly maintain the provenance of the different objects, so the relations of them and where this part belongs. So let's start, and we create an atomistic structure. I now use tab completion, so I hit tab on my keyboard, and I already get a selection of different commands available. And the first one is already the right one, right? So I want to use the ASE package and create a bulk structure. And let's say we want to create an aluminium structure, and then we want it to have a cubic cell rather than the primitive cell with just a single atom. So I create the structure object. I can look at the structure. There are many different functionalities of the structure. The structure is basically based on ASE, so we can check this. It's derived from the ASE class, and you can find more structure tutorials in the designated notebooks here. So I will just keep it short. I already showed you that you can print the structure. I can show you how to now plot it to have like a more graphical representation using the plot3D. Here we use the NGLView library, which allows us to plot the structure directly inside the Jupyter Notebook. So it will take a second, and then we see the structure here. We can rotate this, we can zoom in, zoom out. Obviously it's not so interesting for just a single FCC structure, but you can already imagine how I can work with this structure. Yes, as I said, it's compatible to ASE, so you can also delete atoms, or let's say we can repeat it. Let's first repeat it. Then we use the setRepeat function, so it's in the same object. And let's say we'll make it larger, 3 by 3 by 3, and then plot it again. Just to get a first impression, now we already have a larger structure that we can rotate. We can then say we delete one atom. So again, I use the autocompletion to get all this. I select one atom and del command. Again, we try to as much follow the Python syntax, and the same what ASE does as well. So now having created the structure, we want to start our first calculation. So therefore we use, again, the create job function here. Sorry. And we set the job type. Again, we're using auto-completion. So the goal really was to have as little as possible commands we have to remember and can do as much as possible using auto-completion. You already see, okay, I just type one letter and then it's auto-completing and give me the particular code. Here I select LAMMPS to do some kind of small MD calculation. I can now give it a name. So I say, okay, this is job named LMP, and then I can assign the structure that I just created to this LAMMPS job. Right? So just assigning this variable. And we can start and look for potentials, and typically this would involve looking at something like the NIST or OpenKim potential repository. Here I can just call the load potentials function. I just select the first one, but you can easily imagine that you might want to iterate over different potentials. Select the potential and set it for the job as well. Finally, as we don't want to do just the static calculations, we might also want to run some MD calculation. So I say like calc MD, I select the temperature. Say the temperature we want to be like 800 Kelvin, and we can select the number of ionic steps. Let's say we do 10,000. Good. All this is now a very generic code. So the same code applies. I can use the same commands to run, for example, a DFT calculation with VAST or with our in-house code swings. It would basically be using the same commands. Still, there are certain features that advanced users like to use, which might not be included inside pyiron before. So we can always also access the underlying files, right? So we have the input control file, and those of you who are familiar with LAMMPS will find the familiar commands, LAMMPS command, and then the corresponding parameters. And you can always change them using the dictionary notation. So let's say we want to increase the number of run, and we say, okay, let's do 10,010 steps, right? So I can easily modify this here, and afterwards I just call run, and I directly run it interactively in the same session here. So once the calculation is finished, we can look at the job table. The job table is basically will be our SQL database to monitor the jobs that are executed. And we now say we have one job created in our table. The job status is finished. So we start by being created, and then it's running, and then it's finished and collecting in between if it's collecting the files. We see the chemical formula, so we are only using aluminum atoms here. We see the project where it's executed. We see the name of our job, the start time, how long it took to execute it, where it was executed, the code we used, and then the version of the implementation. Maybe if you want to now change also the version of the executable, we can also look at this. So we can take the executable, we can directly see, okay, what is the path? That's maybe also interesting for people who want to modify this or adapt it for their own cluster, so they can look at this and get the input, and basically inside the shell script we're just calling the executable like this. So if you need to load some specific modules or you want to modify this, you can easily do it also. The good part about pyiron is really you just set it up once, and then everybody on the same cluster can use the same executables that you created. Inside pyiron you can then also list multiple executables, and here I just have one. I have it also available with MPI, so I could also redo the same calculation just selecting more cores. This would be done by using the server object, so we could say server cores equal to. Obviously on my binder the resources are a bit limited, so I don't repeat the calculation here at this point. But I guess the important part is we now already talked about the input parameters and how the user can set the input and even customize the input here. We also talked a little bit about the server object, how you can select executables and cores, and the same would apply for queuing systems. So let me now jump and look a bit into the output. We always use edge brackets here. So the output, again, we have the output structure, so the structure at the end of our calculation. We can also look at the generic part. The generic part is again the output that we create for all codes, and let's say we, for example, look here at energy total, and you can see, okay, it returns a NumPy array. It's not so easy for us to understand what's in there, so we now import our matplotlib. We say it to be inline inside the Jupyter Notebook and import plot as plt, and then we can directly plot it. Right, so we can take our area, and that's the advantage here. There's no more parsing needed. We get how the total energy is changing, and if you want to make it a bit more nice, we can add like labels. This would be time steps, and then say y label energy. And then we could also say we want to plot this directly with looking like in comparison to another quantity. So I guess we have the steps also in there, right? So we can plot over the steps as well. So let's put this in here. Right. Yes, and if I mistype it, it can't plot it. But now we really have the right time steps there, right? So we really see it goes to 10,010 steps, just like we want it to be. But so that's really the first entry, everything. So typically pyiron takes the output files and stores them as HDF5 file, and then we can very easily access them like this. If you need any special property from the output is by default compressed. We can see this if we just look at the working directory. So this is our working directory. Again, typically the users don't need this, but here I just show it for demonstration purposes. We can look into the working directory. There's a compressed output file. We can then directly from the notebook, we can decompress this, and then we can access the output files as well. Right, and you see the underlying LAMMPS output. So if you have a tool which adds any additional output to LAMMPS, you can also add it in here, right, to have an additional parser, extend the existing parsers to parse for additional properties. So we now did a very first calculation. So I guess the next step, maybe we should name this a bit. It's, again, the advantage of the Jupyter Notebooks, so that we can already insert the documentation. So here we talked about a structure. So we name this chapter structure. Then here we started to create our first LAMMPS calculation. And let's say we call it LAMMPS MD. And then we know we were talking about molecular dynamics. And here then we started to look at some plotting. And maybe we also want this to be like a subchapter, so we can add like another, right? It's full markdown based, so you can have arbitrary levels of indentations and so on. Good. The next step is a bit, okay, how can we now, having a single job, you can already imagine, okay, how you can combine different kind of protocols, for example, to validate interatomic potentials, but there are common calculations that you maybe want to repeat over and over again, right? So let's say we want now to calculate energy volume curve, volume, and so we create a new part here. Good. So we can start, we create a structure. Here I just again use the ASE bulk function. I again create an aluminium structure. But this time I just take the primitive cell so we can be even faster in terms of calculations. And now we want to follow, or let's say we want one job template, so we create too fast. Let's say we want the job. We can create the job. again using LAMMPS. And we name the job. Yeah, let's say we do a for loop over different strings, right? So that's something we can easily do. Strain list. This goes lints. NumPy first. P, and then we can do a lint space. From 0.9 to 1, and let's say we do 11 steps, right, and we can plot our strain list afterwards. Right, so this would be the different strains we apply on our structure. We can then have our template structure, so we can create a new structure. Strain equal the copy of the original structure, and then we just strain the cell, and then we just say, okay, scale essence equal true, and yeah, we just give a new cell here, and the new cell is going to be our previous cell dot cell multiplied by our strain. And so just for this example, we now take we set the strain to, let's say, 0.9. We execute it, and we can then compare the two structures. And we can see, okay, the position of the atom stays the same, but basically just the cell is strained by 10%. To confirm that this is working. And now we would construct basically a for loop. So for strain, the strain list, we would always copy the structure. We would then apply the strain on the structure. And we would create a job. And the job name would be strain. And then we would do a string of the strain, and then we have to remember to replace the dots, and we just replace it with an underscore. So now we have our job names, and then so the job structure again being the updated structure that we just created with the strain. We select the same potential like we did before. So we did this here. And we just do a static calculation. So here we just call the run command. And that should be it. Yeah, we maybe want to collect a bit of different values, right? So we want to have like a volume list. Or no, maybe we just execute this. So then we can do. Okay, I made a mistake, and it already says, okay, which line I made it wrong. I have to name the variable correctly. Then we take a look at the job table again, just to see that this is coming, and then we will iterate the same code again, and collect the list for the volume list, which should be empty in the beginning, right? So you see it was doing all the calculations, all of them finished, they basically took no time, and so on. G, an energy list, and now we always take from a given job, so we take volume list, and here we append, so we can take another look at this, but basically it's output generic volume. Yes. So the volume, and we just take the last value there. So let's say -1. And the same applies for the energy, and we just select the total energy there. So just to check this again, tot, and we get the total energy. And also here we need the last value, like this. The important part now is if I execute exactly the same commands again, it's not creating any new calculation, but it identifies the jobs based on their job names and sees that they were already calculated. So it's just reloading the same jobs. So if you want, okay, the jobs are existing, it's just reloading, and we get the same results in here. Take a second, and we will just make this a little faster in a second. And so now we can plot this data. Let's plot again. We plot our volume list and the energy over volume, and we get our nice energy volume curve, right? So we can already say, okay, where's our equilibrium volume, and then calculate the bulk volume just by fitting it or something like this. Right? So again, we should maybe add the labels. So the X label is the volume, and then on the Y label, we have the energy. That's very nice. So, good. So the next part is we can already accelerate this part to make it a bit faster, the calculation. The first part we can do is, instead of this line, we just remove this line here. We just say, instead of trying to create it again and running it again, we just call the inspect mode here and give it the same job name. So again, we use the job name as our universal identifiers. And then we can also skip these lines, as well as these. Alright, so we really come down to just 3 lines, and it's already much faster. And we get the same result, the same data. So this really allows you to separate the calculation and the analysis in like 2 separate steps. So typically we would say here that the calculations are submitted to the queuing system, so it would take a longer time, and we can already continue working on our calculation on the post-processing, and then just reload the objects in this inspect mode to be very fast afterwards. Another one, as we typically calculate quite a lot of these energy volume curves, it's maybe also interesting to just be able to calculate them directly. Right? So we create now, let's say we just save this energy volume curve, make a new subchapter here and say, okay, this is individual jobs. And now we have something like what we call meta jobs. And meta jobs are basically a combination or an object which includes multiple objects itself. So that's what I will do here. Meta jobs. So I can set this up. Again, I create a template job here. So I'll just give it the name here, template, so we don't have to set any strain. That's the same template I'm going to use for mine. We don't want the strain structure. We just want one structure. I'm going to use this template for all the following calculations. So then I can, from this job object, I can create a new object. And I use the same command as previously. So pyiron, and then I create the job type. The Mardigan object is the name here. Marn. And the Mardigan object itself also has some inputs, so we can set the number of points, the kind of fit procedure, the fitting order, and then also the volume range. I don't change any parameters here, just for the test. I can just execute this, and you see it automatically creating the jobs, naming them by different strains, and then iterating over all these calculations. And then if we do this, the advantage of these objects is that they also already come with built-in plotting and fitting functionality. So you get a lot more. If it's like a typical thing that many people do, it makes more sense to do this kind of meta jobs. If it's something new that you want to develop or you want to change something, we always recommend writing your own code and doing the steps basically manually, which gives you more flexibility. Good, now we talked about individual structures in the very beginning, individual calculations, combining calculations in this kind of for loop. You could also now imagine doing the same for loop over different potentials, something like this, right? So we can just change this one parameter here, iterate over other parameters. You saw already the job table and how it's increasing, so maybe take a look at this again. So we see the job table here, we see the different jobs from the two different projects, and so on. Good. One other approach that is quite typical in pyiron is when you have like a lot of calculations, is that you want to do like more like a data science approach to aggregate the data. And for this we have the table object. So again, it's all created from the project. I'll create table. Yes. So I just create my table object here. I say give me, now I define a filter function. So the filter function being filter job. Let's say I want a job, so the job gets as an input, and it should return if strain is inside the job name. Right, so if the strain is in the job name, then I want to include this job in my analysis. So I assign this as a filter function. I just assign this function here. Now in a similar way I can add functions for the analysis. Here I just say get energy, so there are already quite a range of functions available, so it's basically up to you to choose which ones do you want. So I want the energy and the volume. That's what we previously did. So get volume, not Pearson, but total volume. Let's say I also want like another function, like my own function. Let's say job get, or let's say will be a function we could name. You can get the lang of the job name, right? So lang of job name, just some arbitrary function that you might define on your own. Could be anything. Here I just take the lang of the job name to have an easy way or easy function to add. So I take the lang of the job name as another function, and then I can add this to this pyiron object again. Lang of job name. We always try to be a bit more explicit in our function names, then it becomes more clear also for other people who might use the same notebook afterwards. So I now created this table object. I can just run it. You see it's iterating over the objects. It's collecting data from 22 jobs, yes, because we did 11 jobs here and then 11 jobs before, so it should have now 2 Mardigan data sets. We can look at the data frame in terms of like a pandas data frame. We see, okay, the job name and the lang of our job name is there, the volume is there, the energy is there, and the job ID. Right, and we can now plot the very same data, so maybe I want to store this in a data frame object or in TF, and then I could say, again, plot df.chart over volume, right? So that's what we want. And we see, okay, it's a bit difficult from structure here, but you basically see how it's also producing the very same energy volume curve. Right, the important part here is really that it's a different approach. Previously, we calculated first with the, or very first, calculated with the for loop, then we used our meta job object, and now finally we analyze the existing data using this kind of pyiron table object. So maybe I should add another headline here and say, okay, this was a table object. And so based on this, it's really, it's again a different approach. For example, you might have a lot of DFT calculation you want to analyze or that you want to use and develop a machine learning framework. And you would collect the data that you need in this kind of data frame. And with a data frame, from this data frame, you can really use it with most of the frameworks. Good. With this, I guess it's a quick introduction on how to use pyiron and start your first calculations. I'm happy to hear your feedback. And yeah, thank you all for your attention.